Hello all, welcome to the new lecture of this course, Electric Vehicle Dynamics and Motor Drives. So far we have discussed the control of permanent magnet synchronous machine and induction machine. Induction machine, in fact, we have gone on to see the scalar and vector control, both aspects, along with some of the PWM techniques and the analysis of that. Now we are going to extend our study for a particular case study which is related to the railway propulsion system. So there are many features in railway propulsion system which are unique, and it makes a very prime example of how electric vehicles have become popular in the segment of transportation. So we have had the diesel locomotives which were primarily dominating the railway propulsion structure, but nowadays these have been completely, almost 98%, replaced by the electric locomotives. So the structure, if we see broadly what we have in the electric locomotive, we have basically a wagon which is basically having electrical subsystems, for example transformer, motor, power converters, some control units, and the connectors, say pantograph and circuit breakers and all. So this unit basically takes supply from the 25 kV overhead line, and this is a single phase supply. Which is basically connected to the transformer directly, from where it is distributing the power in the secondary windings of this transformer at a lower voltage. So what we have essentially in this structure is that we are finding there are two power converters shown over here, which are little bigger in size, and rating wise these could be something of the order of 3 megawatt each. So, and these 3 megawatt converters are primarily operating induction machines, which are also called as traction motors because of the application, which are rated for nearly 1 megawatt. So this kind of structure is generally used for locomotives which are used for the goods transportation, so WAG 9 or WAG 9H. So we have three motor structure for each bogie. Now there are certain small units of power converters connected over there also. These are primarily auxiliary converters which are supplying the cooling for the motor. So these are connected to the blowers which are supplying air to the traction motors, and also the battery bank which is used for providing power to the control unit. So this battery bank gets charged by the auxiliary converters. So in railway infrastructure or in railway system, what we find very usually is that these are kind of having redundancy. Well, there are a lot of redundancies in the railway structure which is required to ensure that the system is running under all the conditions. So if we have failure of one unit, in that case rest of the unit should be functional, and at least at partial power the unit should be able to operate. So here in this lecture we are primarily going to focus on the bigger unit, which is actually called as traction converter. We will see in more detail what is the structure of the traction converter, what are the essential components, and some basic understanding about how these different units are operating. So as I said, the primary objective of this traction converter is to operate the traction motors, and there are typically for the WAG9, WAG9H structure, there are three motors connected to the same traction converter. The main supply is basically taken from 25 kV overhead line, and from the step down transformer it is taken at 1.269 kilovolt, which is essentially fed to the input of the traction converter. So there are two parallel windings, two parallel secondary windings which are basically feeding the traction converter, and there are three phase outputs. So all the motors over here are kind of three phase motors, each one rated at 850 kilowatt, and the operating frequency or the rated frequency for the rated fundamental frequency for the motor is 65 Hz. However, these motors are generally operated up to 130 Hz fundamental frequency. So the basic structure involves multiple single phase AC converted to multiple three phase AC, and at a variable voltage and variable frequency. So the operation is very power converter intense, which means that the power has to change from a 50 Hz single phase form to three phase with variable voltage, variable frequency kind of structure. So which is why there are several units operating within each power converter. So if we now break this block diagram, the bigger block diagram, into smaller segments, what essentially we are going to have is the structure somewhat looks like this. So the parallel windings of the transformer, secondary windings of the transformer, are basically connecting to rectifier units within the converter, and these are many a times active front end converters. Now of course, because single phase to DC power conversion is involved, so these are single phase active front end converters. Now this power which is coming in form of single phase AC gets converted to DC at voltage level which is approximately 2800 volts. So the single phase active front end converters are operating in parallel. So the output of these converters are connected across the same capacitor bank, and the conversion is happening such that the power is shared between the two converters. Now, because we are dealing with single phase to DC power conversion, there is possibility of generating 100 Hz component on DC link. Now this 100 Hz component must be filtered out before we are ready to use this DC for the further processing. So we are connecting a 100 Hz LC tank tuned at 100 Hz to filter out the components which are associated with the 100 Hz frequency. So this LF and CF are designed in that manner, and many a times LF is actually part of the transformer. So there is a dedicated winding provided on the transformer that is basically operating as LF, and on the traction converter usually only a capacitor bank is installed, that is basically called as the filter capacitor bank, which is connecting in series with the filter inductor. Now this filter basically makes the DC bus voltage relatively smooth, and it is ready for further power conversion to three phase AC. Now going ahead, we have the possibility of regulating the DC link in case the voltage value goes higher than the desired value. So for example, the nominal value of DC link for most of the systems is kept at 2800 volts, which is actually designed according to the voltage rating of the AC machine. However, there is certain range which can be provided. For example, say 1300 3100 volt 3.1 kV, up to which the converter is safe to operate. However, if the DC link voltage is somehow crossing this limit of 3100 volt and the front end converter is not able to regulate, not able to bring down the DC bus voltage to the set value, nominal set value 2800 volts, then in that case we are having brake chopper unit installed on the same converter, which basically brings down the voltage by exhausting the stored energy in the resistor bank. This register is commonly known as brake register. So we'll see one by one how these units are designed and how these are connected in the schematic. But broadly, let us try to understand the components first. Now, the brake register or the brake chopper operates until the value comes back, the value of DC link comes back within the safe operating limit of the DC bus voltage. Further, this DC voltage is, the DC link is connected to 3 inverters which are operating independently, which means that the dynamics or the control of the motor 1 is only controlled by, say, inverter 1. There is no impact of any change in the speed or dynamics on the other unit. So even if one unit is going faulty due to some reason, the other 2 units are still available for operation. So these units are independent with respect to each other in terms of operation. Now, this voltage 2800 volts is basically converted to 3-phase AC through a 3-phase inverter, and typically the fundamental frequency is operated or taken up to 130 hertz. Now, what may happen is that because we are dealing with the converters which are now having a power of, so say, a megawatt level or 1.5 megawatt level, the semiconductor devices may see huge switching energy losses, which is why many times switching frequency for the devices which is primarily IGBT is restricted to a low number. So for example, typically the active front-end converter may have switching frequency restricted to, say, 250 hertz, whereas the inverter may have switching frequency restricted to 500 hertz. So these units are designed in a manner that the loss occurring in the devices are effectively taken out through the heatsink, and the junction temperature does not exceed the desired limits or the design limits of the unit. So this is how the basic functionality of this system is going to be. Now, if we talk about the supply that is received from the 25 kV overhead line, the frequency, nominal frequency is 50 Hz. However, as per railway guidelines, the frequency may vary by plus minus 8%, which means the converter should be capable of operating over a frequency range of 46 Hz to 54 Hz, where 50 Hz being the nominal frequency. Similarly, the nominal voltage also may fluctuate. So we have the nominal value of voltage taken at 25 kV, the range over which the converter should operate comfortably and without degradation of any power is basically varies between that range varies between 24 to 22.5 kV to 27.5 kV. Whereas occasionally the voltage may fluctuate on the higher side up to 30 kV and on the lower side it may fluctuate up to 17.5 kV. So suitable degrading factors may be considered to curtail down the power. Now if we plot the power versus the voltage, we are going to have constant power around the nominal voltage and the variations which are generally expected 22.5 kV to 27.5 kV. Whereas as we cross this limit, we need to degrade the power. So we may need to switch off the operation if the voltage is crossing on the lower side below 17.5 kV or on the higher side above 30 kV. So this is one typical power profile how we are going to have in the real life scenario, in the practical scenario for the propulsion system. The same reflects on the secondary voltage of the transformer also. The nominal value 1.269 may generally fluctuate to a value which may be something around 1000 volts on the lower side, and on the higher side it may jump up to 1300 volts or 1400 volts. Now when we are saying that power is not degraded for this range, which means that the converter should be capable of supplying full power, which means the rated power up to the 22.5 kV voltage, which means the current is going to be on the higher side. So I max can be calculated as P rated by V min. So usually our converter should be capable of supplying this much current through the active front end converters. Now if we see on the output side, the motors, typically a 6068 motor manufactured by ABB is used for the railway propulsion. There are many more manufacturers also for this motor nowadays, and the typical power rating is 850 kilowatt. Now the nominal voltage is somewhere around 2.2 kV. So the DC link voltage minimum value can be computed to be nearly 2800 volts, and that is why we are arriving to the number 2800 volts for the VDC. The nominal current for the motor could be somewhere around 270 ampere. So this is the continuous current rating where the motor should be able to operate for the say longer number of hours. So the RPM according to the rated fundamental frequency is given somewhere around 1283. So this gives us information about what is the slip speed of the motor and how rated torque can be computed. However, the motor and the converter should also be capable of operating at the higher torque ratings for a short duration of time. So that is why we have 1 hour rating provided over here with slightly higher current, and a short term power rating with a 370 ampere current value, where it should be able to sustain that current rating and the increased torque for few minutes. So this is how the output is expected to be. Many a times this motor, which is rated for 65 Hz, does operate for almost 130 Hz fundamental frequency as suggested earlier to achieve the speed of 100 kmph for the goods locomotive, 9 or WAG 9H. Now we have other units on the electric locomotives. For example, we have passenger trains, say WAP 5 or WAP 7. Now these involve basically a different type of motor, a slightly higher power rating motor 7059, where the power is going up to 1.15 megawatt, and these are having a rated frequency of 80 hertz, which again is required to operate up to 160 hertz fundamental frequency. We have the higher current rating given over here also, which is the continuous duty for the motor, and the short term duty for the motor is also provided over here. So these basically give us the capability of the motor up to which our converter should be able to operate the system. Now let us take a quick look at the tractive effort required from the locomotive when we are going for the maximum torque and maximum speed operation. So what we find is that the tractive effort basically changes with respect to the speed as we are running the locomotive. So it has the maximum value when it is operating at lower speeds. So up to say 50 kmph, we have a continuous constant value which is somewhere around say 32 or 35 tons, and then the locomotive should also be capable of operating at short-term duty as suggested earlier for the motor, and this is where it decides the maximum capability of the locomotive, which basically is going nearly up to 52 tons. So for a lower range of speed, somewhere around say 30 or 32 kmph, this should be able to generate 52 tons of tractive effort. Now this translates to the motor torque requirement in terms of Newton meter. So the rated torque for the motor is nearly 6000 Newton meter. That is under the normal operating conditions when we are supplying the 270 ampere rated current. Now once we talk about the upgraded or short term duty, this value corresponds to 9000 Newton meter torque value for each motor. So the motor drive should be capable of providing 9 kilonewton meter torque at the initial stage, at the starting of the locomotive, to overcome the inertia and then accelerate at a consistent value. So further, what we find that the value of the tractive effort reduces, and so the torque value required from the motor also reduces, and it settles down to a much lower value near the highest speed. So somewhere we find that near 50 kmph, the frequency, fundamental frequency of the motor touches 65 hertz, and after that we need to have the field weakening operation for the motor for taking the speed further. So which is why we have degradation in the torque value, and hence a reduction in the torque is seen over here. So the drive should be capable of operating this characteristic completely for the given speed range. Now when we are trying to stop the locomotive while it is running at a speed, we generally need to have regenerative braking of the system, which means the mechanical kinetic energy has to return back in form of electrical energy to the grid. So which means that we also have power, we may have power coming back from the motor side to the DC link, and this is where the scenario of DC link voltage going above the safe operating limit may occur. Now there are certain limitations. We cannot have braking at a at any value of no power level. We need to have restricted value for the regenerative braking, and this is what is given by the braking effort from this chart. So as we are moving for the lower speeds, we have higher braking effort given, and as we are having the higher speed, because we cannot generate a very high value of torque because of field weakening, so we have reduction in the torque value for the given system also. So with this, we are able to understand that the motor drive should be capable of generating the torque which may reach up to 9,000 Newton meter, which is almost 50% more than the rated torque value of the induction machine, and it should also be capable of changing the value dynamically. So now let us try to understand the operation of this whole converter in little bit more detail, and we have a typical schematic diagram for the traction converter where we are having different units shown over here in the shaded form. So what we have essentially, as we have suggested, that the active front end converter is processing almost 1.5 megawatt power, and this is single phase AC, and many a times the voltage may dip on the lower side up to 22.5 kV. So which is why the current may reach up to somewhere around 15 to 1700 amp, considering the ripple and other factors over there. So usually the design of the active front end converter is done in a manner that parallel IGBTs are operated together for sustaining so much current. So what essentially we are trying to have is, we have single phase active front end converter which has H bridge structure, which is connecting the DC link, and then we have the transformer secondary winding connecting to this unit, so this is the structure which is being realized over here. However, each IGBT shown over here, each module shown over here is basically having two separate units. So these two are operated together to sustain the desired current value. So what essentially we get to achieve is that through these two gray blocks we are having the first single phase active front end converter. Similarly, the next two blocks are giving us the second single phase active front end converter. Now there are certain more things which are happening within the system, and we need to prepare our system before we can start any operation on the front end side. So there are two more units which are connected between the secondary winding of the transformer and the traction converter. So first one is basically a pre-charge circuit. So when we are starting, the capacitor voltage would be 0, which means that if we are trying to turn on or connect the winding directly or connect the supply directly to the converter, there may be huge inrush current and that may damage our capacitor bank. So which is why we need to have some kind of additional resistance kept in the path, and a small contactor called as pre-charge contactor is placed here, and the resistance is called as pre-charge resistance. The value of the resistance can be computed on basis of how much current we can comfortably allow within this unit based on the current rating of the capacitor, the cables, the IGBT, etc. Now, the first action what is taken for starting this system is that we turn on the pre-charge contactor and allow the DC link to charge. Now, once the DC link is charging, we cannot have this pre-charge capacitor connected always in the circuit. So which means that at some point of time, we need to disconnect this from the circuit, or we need to shunt it out from the circuit by having another contactor, which is essentially called as the main contactor. So once we close this main contactor, the current will effectively bypass the pre-charge contactor and it will flow in the wires. Now, because there are two front-end converter units as shown over here, 1 and 2, pre-charge can be connected to say only one unit. However, the main contactor must be connected to both. So pre-charge contactor is typically a single pole contactor. Whereas the main contactor is a two-pole contactor which is effectively connecting the line of each converter with the transformer secondary winding. So transformer windings can be shown over here. Now it must be noted that the transformer is especially designed to have additional leakage value in the secondary windings or in the transformer, so that there is no need of connecting any additional boost inductor over here. So typically the leakage inductance value for this system is somewhere around 2.1 millihenry, and which is where this acts as the boost inductor for the further operation of the active front-end converter. Now, these two active front-end converters are also operating independently, which means these are having their own independent controller units for providing the command, the gating signals to individual active front-end converter. Now, in case of any fault or any trip in one of the converter, the system can be supported with partial power, and that is the main point, or that is the importance of having independent units over here. Now, as we proceed further, we may take a look at how the DC link voltage and AC side current and voltage are going to look like for the active front-end converter. So as I suggested, there are several stages within the operation of the active front-end converter. So what we find over here is that initially the voltage, which is at zero value, is rising, and then almost settling to a value from where there is small transient involved over here, and then a ramp is given in the DC link voltage, and then it is settling to the final value, which is the desired value, 2800 volts. So these are basically corresponding to the different states what we are having. So the initial first stage is basically related to the pre-charge operation of the active front end converter, where it is allowed to charge through the diode rectifier available on the same unit, and then we have the operation of main contactor closing. Now once this operation is complete, then we go for the remaining action of the active front end converter, where we are doing the voltage boosting. And the voltage value is taken to 2800 volts. So the action taken by active front end converter is to only maintain the value of DC link at the given reference value. If there is any outflow of power from the active front end converter from the capacitor link, so if there is any power flowing out from the system, the active front end converter basically takes the corresponding power from the grid and fills the capacitor bank with the required energy value. So that is how the DC link voltage is maintained at the same value. In case of regeneration, when the motors are providing power back to the electrical system, to the electrical unit, the capacitor voltage tends to go higher, and then that is where the power from the active front end converter is pushed back to the grid, and this is again taken back to the nominal value. So that is how this operation, the control operation, is coordinated in terms of power. So while operating the system, we also need to ensure that each unit has a coordinated way of operating, and the power taken or absorbed by any unit is not unnecessarily high or very fast. So we can have a smooth operation of this exchange of power. Now moving to the next unit, we have the brake register shown over here connected to the brake chopper unit. So I can mark it with the red box. Typically it's a half H bridge structure where we have a big resistor bank which is having a nominal value around 1 or 2 ohms. However, the power rating is pretty high, is basically used for discharging the DC link through the top device. So in case there is any surge in voltage beyond the safe limit, the top device is turned on and this DC link can discharge through the brake register. Now the filter, as suggested earlier, is shown on the left hand side of the circuit. This basically removes the 100 Hz component from the DC link. Then we have set of bleeder resistors also connected over here. These may also be called as earth resistors. So what we find is that the midpoint of this is basically connected to earth. So this is one of the safety points what we have with the converter is, if we are measuring the voltage of both the sides of this resistor with respect to earth, these should be balanced, which means that the DC link should be equally, the voltage should be equally distributed on both the resistors. If in case one of the voltage is going higher and say this V upside and V downside, if there is any difference between these two, which means that there is some problem with the earthing of the system, or there may be some leakage current flowing in the system, which needs to be rectified before we resume the operation of the converter. So we have to ensure that the V down and V up are nearly similar. Now going ahead, we have the motor units, and as suggested earlier, typically we have the two-level inverters deployed over here. So we have three-phase inverters shown in the shaded block over here. We have the outputs we can write as RYB for each one, and these are also controlled through independent control units. Now it should be noted that when we are trying to operate the active front-end converter, we are desiring for unity power factor and good current quality. So the unity power factor can be achieved through the control. However, the current quality is basically affected due to low switching frequency. So which is why we have a lot of ripple coming on the line current. However, with operation of multiple active front-end converters in parallel and with use of certain more filters installed on the transformer, the quality of the current on the primary side can be maintained at a reasonable value. The same is reflected on the motor side. However, on this side, we are not very much concerned about the quality of current, as in the THD could be higher. However, we need to ensure that it is not resulting into torque ripple or torque harmonics which are going beyond a very unsafe limit. So, which is why we have several PWM and control techniques given over here for doing such mitigations. So now if we see the torque demand and torque generated from the system, from the motor drive, what we have earlier said that we are required to generate almost 9 kilonewton meter torque in the initial phase of the speed, and because we are operating with low switching frequency, the ripple coming on the electromagnetic torque generated by the system could be quite higher. So what we see over here is that the drive is able to follow the reference torque provided by the system. So initially the torque is at 9 kilonewton meter level and then slowly reducing to 7.5 and then gradually reducing to lower values as the speed is increasing. So same thing can be seen on the current in terms of the ripple coming on the motor line current. So because of this, again, restricted switching frequency operation, we have high peak to peak ripple. However, the traction motors are designed generally to bear more harmonic distortions, which means that it can sustain more harmonic losses and can operate at higher elevated temperatures. Now the switching frequency of the motor is not a constant number as we are talking about the complete range of fundamental frequency. To maintain the quality of current, to maintain the torque pulsations, we need to have operation of this system, of this motor drive, with a variable switching frequency kind of system. So we are trying to have synchronized sine triangle or synchronized optimal pulse width modulation techniques for operating this system. How we are starting is basically that in the initial stage, while our fundamental frequency is lower, we are bound to provide very high value of torque, which is where it is suggested that the value of switching frequency can be kept at a lower value and then gradually maintaining a constant pulse number. For example, pulse number of 15 can be kept over here. Now, because there is limit on the maximum switching frequency what can be tolerated by the system, as and when we reach the maximum switching frequency, we have to switch back to a lower pulse number. And if we refer back to our previous lectures, what we understand is that there are discrete pulse numbers at which the synchronous sine triangle can be operated. So we have 15, 9 and so on. And then when we are including the synchronous optimal pulse width modulation technique, we can have the odd non-triplet pulse numbers as well. So pulse number 7 and 5 can also be included over here. So this is one example of how the pulse width modulation technique can be utilized for operating this induction motor drive, which is having high power and restrictions on the switching frequency are so stringent. By having this, we are able to maintain the thermal losses within the device to a lower value, and we are also able to contain the peak to peak ripple coming on the torque within a lower value. The distortions on the current, as we are reaching to the highest frequency, we are finding that this is going closer to the 6-step operation sort of current. Now, once we have understood the basics about this system, the other hurdle what usually industries face is basically after designing, we need to have a method to test this whole structure. Say we have designed the traction converter and we would like to have testing of the same, but because this is rated for 3 megawatt, it may draw that kind of power from the utility grid, which is not generally recommended. So we cannot have 3 megawatt power drawn from the utility grid just for testing the unit which is there. So which is why we need to have a method called as back-to-back power circulation method, where we are connecting two similar units and we are having say 6 motors in place. So the first unit, say unit 1, which is also unit under test, is basically operating the motors according to the desired dynamics what is expected from the locomotive, and these motors are basically loaded mechanically from the equivalent generators. So these are essentially also the same motor which are acting, same machines which are acting like generator and taking power back to electrical, which is again pumped back to the grid through a similar unit. So what we are basically able to test over here is that the unit is able to operate the motors at desired torque level, and the unit is also able to regenerate power back to grid so that all the desired operations for the active front end converter and motor unit are basically covered within one structure. And in doing so, because the power is circulated within this unit through the transformer, we are only drawing the losses from this utility power supply. So typical numbers which are mentioned over here is that we may somewhere require nearly 500 kilowatt of power for testing this total 3 megawatt unit. In fact, when two are being tested, the total capacity goes all the way up to 6 megawatt. So this is the advantage of having this kind of infrastructure. We are able to test all the capabilities without imposing so much burden on our utility grid. So this is all from this lecture, and one of the case study where the electrical systems have successfully replaced the mechanical counterparts, the diesel IC engines, and we have successfully migrated to a very clean and efficient structure with electrical machines and then power converters. So thank you very much for attending this lecture.